This lesson is on numerical integration. Finding the value of a definite integral, estimating the value of a definite integral under a curve by using formulas for rectangles or for trapezoids or in one case parabolas. We're going to estimate the area under a curve without using the fundamental theorem. And there are three ways that we can do this, or three ways that we're going to talk about. And this is mainly used when you can't use the fundamental theorem, meaning you don't know the antiderivative of the function, of the curve, or you don't even have an equation for the curve. You just have a set of points or a set of data, and you're asked to estimate the value of the integral. So you're going to have to use some method. The first method is using Riemann sums, where you use a rectangle to estimate the area under the curve, either lower sums, upper sums, left-hand rectangles, right-hand rectangles, midpoint rectangles. But the idea is you're using rectangles to estimate the area under the curve. The second method is what's called the trapezoidal rule, which is just like it sounds. You're going to use trapezoids to estimate the area under the curve instead of using rectangles. And the third way, which we're not actually going to talk about in this section, but I do want to mention, because you will see this in the Calc 2 course, is Simpson's rule. Simpson's rule is another similar idea, except in this time, instead of using linear functions, rectangles or trapezoids, where you have all linear pieces, you're going to use quadratic functions, second-degree functions, or parabolas, where you're going to have a curve. The idea behind this progression is that you get closer and closer to modeling the curve, to that top being the same as the curve, and therefore you're cutting off less area or adding on less area. So you can see a curve here using a Riemann sum, using rectangles. You go over top here, you're pretty good here, you're under here, you're cutting off a lot here, cutting off a lot here, and you got more over top. If we go to a trapezoidal rule, now we're still going to use intervals. We're still going to go straight up, but now instead of going straight over or straight over from one side to the other, we're going to go from point to point. And you can see how this is way better, or way closer to the actual area under the curve there, because it kind of goes along that curve. Here in this case, both heights are the same at each end point, so it is going to end up being a rectangle, which is just a special type of trapezoid. And then these other three integrals you see. The trapezoid connecting these two endpoints models the curve a lot better than rectangles do. In the end, the idea is the same. As these intervals get smaller and smaller, either way, you're going to be cutting off less and less. So eventually, as your intervals, the space between these goes to zero, either rectangles or trapezoids, your area, your estimate is going to come out to be the area. The limit will come out to be the exact area. But the idea behind the trapezoidal rule, or a key concept or a key part of this trapezoidal rule, is it gets you a close estimate a lot quicker. You can use less trapezoids and get a lot closer approximation than it would take if you're doing rectangles for the majority of curves that you're going to work with. So a trapezoids, or using trapezoids, or using the trapezoidal rule to approximate area gets you a lot closer, a lot quicker than Riemann sums. So right here we just have an example. We don't even have a function. We just have a curve. And we're going to use 4 trapezoids to estimate the area of this curve between 1 and 5. So you have a width of 4. If you have a width of 4, you're going to use 4 trapezoids. We'll make them all the same width. Make them all 1 wide. Now, it doesn't have to be the same width each time, just like with Riemann sums. It doesn't have to be. You usually do make them the same width, but it doesn't have to be. You could make the widths different, like in the first example, or this diagram here. You can see these widths are different. So it depends on the problem. But for the most part, if you're asked to find or use the trapezoidal rule, you're going to split them up into even spaced trapezoids. Area of a trapezoid, we've touched on before. You should remember this from your geometry course. You're going to average the bases and multiply that by the height. So you add up the 2 bases, divide by 2, and then multiply in trapezoids where the bases are the top and bottom. Well, now the bases, the parallel sides, are the sides here, the left and the right. So these are our two bases, and our height between those bases is whatever that width of each of those is. So for each of these trapezoids, I'm going to do 1/2, because that's the formula. Height here plus height here, times the height of the trapezoid, times the width of the interval. So each of these is going to start with a 1/2 and going to end with a 1, because they're each 1 wide. So the height of the trapezoid, because these are the parallel sides, these are the bases, the height of each of these is 1. So I take the value of the function at 1, which is about 5. Value of the function at 2, it's about 7.5. So 1/2 times 5 plus 7.5 times 1. Now I do it again. Add up the area of the second trapezoid. Same thing. The height here plus the height here will go inside. 1/2 average of the bases times the height of the trapezoid. Same thing here, same thing here. So I have 4 trapezoids. The area of 4 trapezoids, I'm going to add up. My total area under this curve is about 29.25. Same idea as Riemann sums. You take the area of a bunch of things, add them up. In Riemann's, it's rectangles. Trapezoids, it's trapezoids. For the most part, you're going to be given a curve, or you're going to be given an equation, or you're going to be given a table full of data, and you'll be asked to use trapezoids to estimate the area. But we are going to develop what's called the trapezoidal rule using n trapezoids. I usually say, find the value of the trapezoidal rule, or use the trapezoidal rule to estimate the area under the curve, or the value of the definite integral when n equals 4, or n equals 8, or n equals 7, or whatever. That n that they're telling you is going to be the number of trapezoids that you're breaking this into. And if they ask you to use the trapezoidal rule, you're going to be expected to make them equal width. If they say apply the trapezoidal rule, you're going to make them equal width. If they just say using trapezoids to estimate the area, then you don't have to make them equal width. That'd be something you'll see in a tabular data or a table full of values problem. So here's a general curve. And I want to talk about what we would do here. It's always going to be 1/2 out front, and then the width of the intervals at the end. So you're always going to have a 1/2 out front, because that's the formula for area of the trapezoid. You're averaging the bases, times the delta x. So if you see, as we go across here, and this is just for any number, for n number of trapezoids, not this specific one where you have 6 trapezoids. It's just an example you can see. So 1/2 bases delta x. 1/2 bases delta x. Keep going. 1/2 bases delta x. 1/2 bases delta x. This delta x is going to be found very similar to how we found the base of each of the rectangles with Riemann sums. B minus a, the value of the interval, divided by n, the number of trapezoids. So you can factor out of this long summation of 1/2 and of b minus a over n, which is what each of these delta x's represents. Width of the interval divided by the number of trapezoids. So the trapezoidal rule starts with 1/2 times b minus a over n. A lot of times it'll be written as as b minus a over 2n, making this one fraction. But I wanted to write it as the 1/2 times the height of the trapezoid. So you see, it's 3 things being multiplied. 1/2, average the bases, height, which is at delta x, which is at b minus a over n. Now, when we average the bases, you're going to do this base plus this base. First base plus the second base. The height of the function there, so f of x sub 0 times, or plus f of x sub 1, that first number. Then, for the next trapezoid, you're going to do this one and this one. So f of x sub 1 plus f of x sub 2. Then for the third, we're doing here and here. Here and here, here and here. And then for the last one, you're doing here and here. So you kind of see these coefficients here. F of x sub 0 plus 2 f of x sub 1s plus 2 f of x sub 2s plus 2 f of x sub n minus 1, the second to last one, plus 1 f of x sub n. What this is saying is you're going to add up all these values, the height of the function at each of these values. You're going to do the first one, f of x sub 0, only one time. So it's only used for this trapezoid. But f of x sub 1 and every one of these values in the middle, in between 0 and n, is going to be used twice. It's going to be used for this trapezoid and for this trapezoid. So you're going to need this value twice. You're going to need this value twice for this trapezoid and this trapezoid. So each of these middle values gets used twice. The end values only get used once. So this is the trapezoidal rule, the formal trapezoidal rule, where you have n trapezoids, where each trapezoid has a height, or each width, if you look at it like this, is b minus a over n, is that overall integral divided by the number of trapezoids. And then you add the value of the function twice in the middle values, once at the edge. So you get 1/2 height of the trapezoid, b minus a over n, times value of the function at the first, plus twice the value of the function at the second x, plus twice value of the function at the third x, all the way through, and then at the end, plus 1 value of the function at the end point. And that's the trapezoidal rule. Again, trapezoidal rule is used to estimate area under a curve when we don't know the value of the definite integral, when we can't anti-derive, and it also works quicker and with less intervals, less tedious number crunching to use than Riemann sum.